So as I said, if you replace s with any stopping time, you get a different result. For example, this lemma says that if you start from I and the expected time that you start from I and you go there and then you come back, you go there, you traverse the state space and you come back. The expectation of this time, return time, is inversely proportional to degree of the pi of I. Pi of I could be, for example, degree of I over two times number of edges. So, for example, here, if your degree of I is, you have a lot, the degree is too much, is very big. So the expected time should be, we expect that the expected time for return should be very small. Because the expected time should be very small because it has many chances to increase this path. Go there and increase these passes. But if it is very small, for example, 1 or 2, then the expectation is just it couldn't be too much. So expected return to I could not be very much if degree of I, if pi I is very small, is small. As you see, for example, here degree of I is just 2. So we expect that the expected time to come back is very small. And so how do we prove it? So we just set your stopping time to be first return time, Ti plus. This is the first return time. And then just we apply the proposition. It says that if you start from vertex I, the number of visits to j before time Ti plus is equal to pi j ei Ti plus. And we also set j equal to I, so it gives us 1 equal to pi I, because the expected number of visits to I starting from I is 1. And pi I ei Ti plus. And from this we conclude that ei Ti plus is equal to 1 over pi. It means that we have proved this lemma. So your lemma could also be this. Number of visits to j before time Ti plus is equal to pi j over pi I. So here again we use that proposition, and as I said, you just need to replace your stopping time by something. For example, the stopping time that we use is here, we need this stopping time. And then from this we can conclude easily that the expected number of visits to j before time, stopping time, what is stopping time, is Ti plus, is equal to pi j ei Ti plus. And from the previous lemma, we know that this is just 1 over pi I. So it is simplified to pi j over pi I. So these lemmas that in the book of David Aldous are very simple, because David Aldous showed us the importance of that proposition, that if you replace your stopping time by thumb stopping times, then you can create lots of lemmas, lots of results, and you prove it very easily. As you see, it's just one line. And an interesting lemma is the expected number of visits to J before time Ti. So this is equal to, so the lemma says that it is equal to EJTI, EITJ. So now to prove this, we need some stopping time. So our stopping time, first we use the stopping time that says, we take the stopping time as first return time to I. First return to I. After first visit to J. So if you apply this interesting stopping time to that interesting proposition, you get expectation of number of visits to J before S to be pi J E I S. And now it is very easy to show that. So we have proved that expectation of your stopping time is equal to hitting J and starting from J hitting I. And we proved this lemma again. And a corollary is just saying that if J is not I and the probability of Tj less than Ti plus is equal to 1 over pi I Ei Tj Ej Ti. And the proof is very easy. So again, we say that the number of visits to I before hitting J has geometric distribution. And to recall what is geometric distribution, it says that the probability that case trial is first success is probability of x equal to k. If you just look at that Wikipedia, you will say that it's just 1 minus p to the k minus p. Because it's very simple, you don't need Wikipedia as well. Because the first success time, it means the k minus 1th steps, there are k minus 1 number of steps, are failure, and the one after that is success. So this is failure, and after that you get the success. And because they are independent, so you can multiply it easily. And the interesting thing about this geometric distribution is that the expectation of that is inverse to your probability, and we will use it. And the variance of x has an interesting form. So you can use these ideas to prove that. So the number of the expectation of visits, number of visits to I before time Tj is just 1 over pi, but your time to hit J is less than time to return. As you know, I use this fact, 1 over p. 1 over p, and my p is here. Because this is the, if you assume that x is your random variable. So the expectation of that, you can use this formula of geometric distribution to prove this. So I proved it using geometric distribution. Another important lemma is that the expectation of number of visits to j before time TL is equal to pi j ei. First you reach TL, you hit L, and then starting from L, the time you need to hit J, and then minus, if you start from I, the time you need to hit J. And the proof of that is very simple, because you just substitute S by the first return to I after the first visit to J after the first visit to L. So this is your I, this is your J and L. First you visit J, but sometimes here, some path goes there, and then you go from J to L. And just if you apply the proposition again, it becomes pi j times ei TL plus e starting from L time to hit J plus starting from J time to hit I is equal to, you can say that it is equal to expected number of visits to J before time TL plus, if you start from J, here you start from J, the number of visits to J before time Ti. And another corollary, for example, could be the probability that Tj is less than TL is equal to, if you start from I, the time you need to hit L, plus if you start from L, the time you need to hit J, minus if you start from I, the time you need to hit J, over if you start from J, the time you need to L, start from L, the time you need to hit J is equal to this. And the proof of this, we are just using a simple fact. And the fact is the probability that if you start from I of time to hit J to be less than time to hit L is equal to expected number of visits to J before time TL over the expected number of visits to J before time TL. But these are the same things, but here we start from J, here we start from I. So this is just expected TL plus expectation of Tj minus expected Tj over EJTL plus ELTJ. And we proved it very easily. Now I want to talk about fundamental matrix, which summarizes many important theorems, many important lemmas, and it says that the Pij to the T minus Pj. So from here you can easily observe that sigma Zij is equal to 0 for any j, summation over j for any I. Okay, so Z matrix, for example, the ij's entry, you can calculate using this. So this Z matrix is fundamental matrix. And it appears in many results in finite Markov chains. For example, a lemma says that the pi I expectation of time to hit I is equal to Zii. But here your distribution is pi. So we use the proposition again, and but we set S very cleverly. I mean, we first wait time because it is a distribution, stationary distribution. So we wait until it mixes all of your room. For example, the smoke is covered all of your room. So you wait after some time. Let's say time t0. You wait until time t0 to mix, to get to the stationary distribution. And then after that you're sure that you're starting from a stationary distribution. So we wait, if necessarily, until the chain next hits I. And then using the proposition, you put j equal to I and say that pii to the t is equal to pi I t0. Now you start from t0. So until time t0, you're just waiting to reach the stationary distribution. But after that, you're comfortable with saying that, okay, I'm sure that this row you're starting from this distribution, and then expectation of ti, and just let t0, the time that you need to wait, just let it go to infinity. And then from here, a row converges to pi by convergence theorem. And then we rearrange it, saying that pii, I'm just rearranging it, minus pi, because this pi comes here, and because summation creates sum of all of them is 1, and so this equals to pi I E row here, and then ti here. So I just rewrite that to show that okay, we have proved this important lemma. And another lemma says that pi j ei tj is equal to zj j minus zij. Another lemma. And the proof is again simple, because we take j again not equal to I, and then we fix that t0 that I told you, and we define your stopping time very interesting and peculiar. And very interestingly, we can say that S is the time taken by the following three-state procedure that I say. And for the chain start at I, we first wait until the chain hits K. We wait until it hits K. So our stopping time is a little bit complex